All right, this last unit video is going to be a very, very short one, and it's all about nuclear reactions. We've spent almost the entire unit talking about the electrons in the atom. But there's another kind of reaction that also takes place. It doesn't take place very often, but it does yet still take place. And though it is infrequent, it's incredibly important. Nuclear reactions are what we're talking about. Now, nuclear comes from the word nucleus. So when we're talking about a nuclear reaction, we're talking about any type of reaction that involves the nucleus of the atom. So protons and neutrons interacting together. Now there's a tremendous amount of energy stored in that nucleus. I want you to think real quick about the fact that a proton is positively charged and a neutron has zero charge. So how are those things held together in the nucleus? Well, there must be something greater going on. In fact, there is. It's called the strong nuclear force. And the strong nuclear force is exactly as it's described. It's an incredibly strong and powerful force that's capable of holding things together that otherwise would have no business being held together. Think about trying to pick up a milk carton with a magnet. That's very similar to what's going on in the nucleus. Now, the strong nuclear force only works over a very, very small distance, but it is an incredibly powerful force. And when that nucleus is disturbed, that force and that energy is released. This right here is a picture of one of those releases of that energy. The amount of nuclear material in this here would probably amaze you. The nuclear material that made this mushroom cloud probably be no bigger than your standard calculator in terms of the actual amount of stuff that causes this kind of destruction. So the first process we're going to talk about is nuclear fission. Again, that's fission, not fission. Okay, it's kind of like the way you would pronounce it would be what Southerners would do when they go out in the lake. That would be fission. Okay, me from the north, I call that fishing, but regardless. Now, when we're dealing with fission, we start out with one large nuclei, one very large nucleus. We're talking about uranium, plutonium, americium, neptunium, very, very large nuclei. And into that very, very large nucleus, we fire a neutron. And that neutron sets off a chain reaction. The chain reaction breaks apart that nucleus into two daughter nuclei and also sets free 3 neutrons to go break apart any other further nuclei that need splitting. This process results in a tremendous amount of energy given away. This is the means by which we get nuclear power. Nuclear power is a result of nuclear fission. In class, I'll show you a very oversimplified demonstration of this with a computer simulation in which you can actually see that there are actually 2 different types of chain reaction that can be generated as a result of a fission reaction. The other type of nuclear power or nuclear reaction is fusion. Nuclear fusion and nuclear fission are what we're talking about here. Now, fusion is the exact opposite of nuclear fission. In nuclear fission, the longer word, the bigger word, you're starting out with a bigger start material, and you're breaking it apart into smaller pieces, thus releasing the energy. The opposite is true when we talk about fusion. With fusion, we take 2 different small elements, these happen to be 2 isotopes of hydrogen, and we combine them together. And when we combine them together, the resulting atom is much, much larger. Helium being larger than hydrogen. This also releases a neutron in the process and a tremendous amount of energy. This is what our sun does. Now, the catch to fusion is not finding the material like it is for fission. There's a lot of hydrogen out there. In fact, hydrogen makes up over 99% of all of the material in the entire universe. The problem is creating the conditions necessary for nuclear fusion. Fusion requires an incredibly high temperature. On Earth, because we cannot simulate the pressure necessary that's made by the sun, the minimum temperature on the Earth is over 40 million degrees Celsius, which is enough to break through the Earth and melt to the core and cause all kinds of mass chaos. To date, the only nuclear fusion that's been created on the Earth has been attained during a nuclear explosion. An H-bomb would be an example of nuclear fusion taking place in a weapon. An atomic bomb, the classic nuke, is a fission bomb. We'll show you those demonstrations and simulations in class. Hopefully you learned a little bit about the nuclear reactions.